For decades, astronomers believed they had built a remarkably detailed map of our solar system. Asteroids were catalogued, comets were tracked, planets were studied, and countless objects were given precise orbits. But that map had a hidden weakness. It mostly showed us objects that were bright enough, large enough, or easy enough to detect. Then the Vera Rubin Observatory began looking at the sky in a completely different way. Instead of treating the universe like a collection of photographs, Rubin is designed to create something closer to a giant time-lapse movie. It repeatedly observes the same regions of the sky, allowing scientists to detect objects that move or change brightness. And that difference is enormous. Imagine looking at a single photograph of a crowded road. You can see the cars, but you cannot tell where they're going. Now imagine watching that same road every few minutes. Suddenly, movement becomes information. The night sky works in much the same way. A distant asteroid might appear as nothing more than an extremely faint point of light. In one image, it could easily be mistaken for background noise. But when another image is taken later, that tiny point may have shifted slightly. Then another observation confirms the movement. And another one strengthens it. Eventually, what looked like an insignificant speck becomes a real object with a measurable path. This is one of the reasons Rubin is so important. Its early observations already demonstrated how much can be hiding in plain sight. During roughly 10 hours of early observations, the observatory identified thousands of previously unseen asteroids, including several near-Earth objects that were not considered a threat. The important part is not simply the number. It is what that number tells us. The solar system did not suddenly become more crowded when Rubin looked at it. Those objects were already there. We simply had not been able to detect all of them. Older surveys had unavoidable limitations. Some objects were too faint. Others moved unusually slowly. Some were located in difficult parts of the sky, while others could be confused with detector artifacts, cosmic rays, satellites, or atmospheric effects. A single observation can therefore be misleading. Rubin's strength comes from repetition. When the same area of sky is photographed again and again, scientists can compare the images and separate genuine movement from random noise. That creates something previous maps often lacked, a record of change. And change can reveal objects that remain almost invisible in a static image. The observatory is designed to repeatedly survey the southern sky over many years. Each observation becomes another frame in a massive record of how the solar system changes over time. That means an unknown object does not have to announce itself by shining brightly. It only has to move. A faint asteroid shifts against the background stars. A distant icy body slowly changes position. A near-Earth object can move much more quickly. A previously lost object may finally be detected again. Each movement becomes another piece of evidence. But discovering an object is only the beginning. Scientists still need to determine its orbit. One image gives a location. Multiple observations provide movement. Enough observations can eventually reveal a trajectory. And that trajectory can tell scientists where an object came from, where it is going, and how it interacts with the rest of the solar system. This is where the story becomes much more interesting. Because the objects Rubin discovers will not all be the same. Some will be ordinary asteroids in the main belt. Others will travel near Earth. Some will be ancient objects beyond Neptune. Others may belong to populations that are still poorly understood. Many of these bodies are leftovers from the earliest stages of the solar system. They can be thought of as natural fossils. The planets formed billions of years ago from material orbiting the young sun, but not all of that material became part of a planet. Much of it survived as smaller bodies. Asteroids, comets, and distant icy objects can therefore preserve clues about conditions that existed long before Earth looked the way it does today. A faint object detected by Rubin may be tiny compared with a planet, but scientifically it could be incredibly valuable. Its composition, orbit, and movement may help researchers understand how the solar system developed. And this is why the idea of a hidden object is more complicated than it first appears. The most interesting discovery may not be the largest object. It may be the object with the strangest orbit. An unusual path can reveal gravitational interactions, ancient collisions, planetary migration, or connections between different populations of small bodies. Rubin's repeated observations will make it possible to search for those patterns on a much larger scale. Instead of studying one mysterious object at a time, scientists can begin comparing thousands or even millions of objects. And once you have enough objects, patterns that were invisible before can start to emerge. That could change our understanding of the solar system itself. Because perhaps the biggest discovery will not be one asteroid. It could be the realization that the map we thought was almost complete was only showing the brightest layer of a much larger and more complicated system. The solar system, but finding faint objects is only one part of what makes the Vera Rubin Observatory so significant. The deeper mystery begins with the objects that are hardest to detect. Some bodies in the solar system reflect very little sunlight. Others are extremely distant. Some move so slowly that their position barely seems to change from one night to the next. And some can disappear into the background before astronomers have enough observations to determine what they are. These objects create blind spots in traditional surveys. Rubin is designed to reduce those blind spots by repeatedly scanning enormous areas of the sky. That matters especially in the outer solar system. Beyond Neptune lies a vast region containing countless icy bodies. Many of them are extremely faint because sunlight becomes much weaker at those distances. A distant object may reflect so little light that it becomes almost impossible to distinguish from the background. But Rubin does not need an object to be spectacular. It needs to detect a consistent change. If the same faint point appears in several images and shifts position in a predictable way, scientists can begin connecting those observations. The object has effectively revealed itself through movement. And once enough observations accumulate, researchers can calculate its orbit. That orbit may tell an entirely different story. An object could belong to a familiar population, such as the asteroid belt. It could be associated with Jupiter. It could travel through the distant regions beyond Neptune. Or it could follow an unusual trajectory that raises new questions. This is where discovering more objects becomes scientifically powerful. One unusual object can always be an exception. But when thousands of objects are discovered, scientists can compare them. They can examine their sizes, brightness, orbital shapes, speeds, and locations. Patterns begin to emerge. Those patterns can reveal how the solar system evolved. For example, asteroids are not simply random rocks floating around the Sun. Their current orbits are the result of billions of years of gravitational interactions, collisions, and planetary movement. The same is true for distant icy bodies. Their present locations can contain clues about what happened when the giant planets were forming and migrating through the young solar system. So every new orbit adds another piece to the puzzle. But there is another reason these discoveries matter. Not every unknown object is scientifically interesting only because of its history. Some objects matter because of their distance from Earth. Near-Earth objects are constantly being monitored because their future paths need to be understood. Fortunately, the vast majority are not dangerous. But scientists cannot determine the future trajectory of an object they have not detected. That is why finding these bodies early is so important. The challenge becomes even greater with smaller objects. Large near-Earth asteroids are easier to detect because they reflect more sunlight and can remain visible for longer periods. Smaller objects can be considerably harder to find. This means there is still a significant population of near-Earth objects that scientists have not yet identified. Rubin's repeated observations can help change that. The telescope can detect an object, observe it again, refine its position, and gradually improve our understanding of its orbit. The first observation might produce uncertainty. The next observation reduces it. More observations reduce it even further. Eventually, scientists can make increasingly reliable predictions about where the object will be in the future. That process transforms an unknown point of light into something measurable. And there is another fascinating problem. Sometimes astronomers actually detect an object but later lose track of it. The reason is not that the object disappeared. Its orbit may simply have been too uncertain. If scientists do not know precisely where it will appear again, searching the enormous sky for one tiny object can become extremely difficult. Rubin's repeated survey strategy could help recover some of these lost objects. The observatory keeps returning to the same regions, building a long-term record of their movement. This creates something previous generations of astronomers did not have on the same scale. A persistent memory of the sky. Every observation can be compared with earlier observations. An object that seemed insignificant yesterday may become important after several more detections. A previously uncertain orbit can become precise. A faint asteroid can become part of a larger family. And an unusual trajectory can become the first clue to a much bigger pattern. This is why Rubin's mission is about more than simply discovering new objects. It is about understanding relationships between them. Imagine finding thousands of pieces from a giant puzzle. At first, each piece looks unrelated. But once enough pieces are collected, their shapes begin